Okay, let's get started again. So just quickly reviewing some of the highlights from last time. We want to generate text that is reminiscent of Shakespeare. We're going to do this one character at a time in order to make it computationally tractable. First thing we did was we figured out all the different characters we need to work with, called the vocabulary. And then we built an encoder that converts those characters to integers, which we call tokens, as well as a decoder that converts tokens back to characters or a character string. And we talked a little bit about the format of our data. This is essentially what we call time series forecasting. We have a data set that has samples organized across time, and we split that into training and test portions without shuffling, but just with some kind of split. Typically, you treat the most recent things as test and the older things as training. And then for our text prediction, or in this application, time series forecasting, what you usually do is you use a sequence of older time points to try to predict a future time point. So this would be one sample of the data. This is another that used these features to predict this, and so on. And when training, you can shuffle these. You don't have to give your model this sequence that is right shifted by one time point every time. You could shuffle from the training, but you cannot split the data set into training and test by shuffling, because that would be mixing features in training and test. Okay. Then we talked about a pretty simple method called the bigram, which is basically it uses this conditional probability mass function. So if ki is the integer that describes the current character, ki plus 1 is the integer that describes the next character. And so we can make a conditional PMF based on our training data. For every possible current character, we can learn the probabilities across all the possible next characters in our vocabulary. And we can actually store all those values in a matrix, capital P, where the nth row of the matrix is going to describe, that's going to index the current character, and the kth column will index the next character. So here was an example of our vocabulary was ABC. And we have, from our training data, these empirical PMFs, which are non-negative numbers that sum to 1. Then if the previous character was A, you have, these are all the possible next characters, and these are their corresponding probabilities. And when we generate text in this autoregressive manner, that means that if our current character is A, we would randomly sample from this PMF, meaning 80% of the time we would draw a B, 10% of the time we draw an A, and so on. And then we would use that as the next character in the generated sequence. So maybe we drew a B. So now for the next step in the generation, we use B as the current character, and then we would sample from this PMF. And maybe we draw C. And then for the next time, we use this PMF, which is what we use for current character C, and we would sample this and continue this process as long as we want. So that's the autoregressive approach. We compared to some simpler baselines, just generating uniformly or according to the prior PMFs, and we see that this bigram, while it doesn't work that well, it at least gives us, it generates things that look kind of like words. There is typical combinations between consonants and vowels and spaces and carriage returns. Whereas if you look at uniform PMF or this empirical prior, you get things where you have like punctuation, as the first element of a word, stuff that's just clearly wrong. So even though this isn't great, it's definitely an improvement over these simpler approaches. So that is the bigram. So then we said, well, can we apply MLR, which is an approach that we've learned about. And we said if we're going to do this, because the feature, which is the current token, is an integer category, we really need to treat that as a categorical variable, and that the way we have talked about doing that is to use one-hot coding. So we can make a vector that I'm calling boldface delta here, which is going to be a one-hot vector, which has the non-zero element, or the 1, at the kith position. So we're now coding the current token value by a one-hot vector, where the 1 is in a particular position. So now that's our feature vector, what we usually think of as x. And so if we want to do MLR, then we create these output scores using, this is like the K versus rest approach. If you hypothesize that the output is in K, then you build weights and bias for K versus not K, or K versus rest. And using the bias and the weights, you compute this linear score, which is just a real number. And then you, these scores are real numbers, they can be negative. So then you need to, if you want to turn them into probabilities, you put them through a softmax. And that normalizes them in such a way that they all are non-negative and sum to 1. And now we can write the PMF. So this is what basically MLR does. And if we, so usually traditionally we call this Y, but now the target we're calling KI+1, which is the integer token at the next time. And if we make these substitutions, then we find out that MLR is really nothing more than the bigram. It's just that it's represented using these coefficients, the W coefficients of the model, the weights of the model, which you can also think of as logits, which are the real number inputs to the softmax. So basically this bigram idea is really the same. It's equivalent to using multinomial logistic regression just based on the previous one-hot coded character. So that's the next thing we figured out. And then we considered, and then we compared computationally. We found, yes, we're getting almost exactly the same PMFs, whether we use empirical fitting or whether we train the bigram to minimize cross-entropy on the training data set. And we talked about the n-gram, which is like an extension of the bigram which uses not just the previous token, but the previous t tokens, where t could be any integer or any positive integer. But the problem with this is the number of PMFs that you would need to compute quickly grows out of hand. So the number of possible combinations of these integers is going to be n to the power t. And so because we have a PMF for each one, we have n to the power t+1 different parameters we need to learn and store and use and all that. And you can see that even for very small block sizes like 3 and a pretty small vocabulary size like 65, we get into the millions and billions of parameters very quickly. So the n-gram doesn't make sense. So the next thing we talked about was token embeddings. And we said, let's think back to MLR, which essentially what it's doing is it's taking this integer between 1 and our vocabulary size n, and it's coding it as a vector in Rn. And the particular coding it's using is one-hot coding. And if you visualize one-hot coding in Rn, or this picture is for n = 3, each possible vector is orthogonal to all the others. That's what one-hot coding does. But you can also imagine assigning different vectors than these for this character, and that is the idea of embeddings. So an embedding, it just says, when I see token value k, I'm going to encode that in some d-dimensional R space as the vector ek. And the size of the space D is something we can choose, and the actual vector that we assign for token value k is something that we can choose or learn. So this gives us a lot more flexibility. For example, we could choose vectors that are much smaller than dimension 65 if we wanted, or much larger if we wanted. And the vectors that we're using are not necessarily orthogonal to every other vector, which makes sense because if you think about vowels, vowels share some commonalities with each other that are different from consonants. So it seems like their embeddings should be more aligned. They shouldn't be perfectly orthogonal. You could say the same thing for punctuation and so on. So the idea of embeddings at a high level is just a way of mapping integers to real vectors, where you can choose what vector you're using as well as the dimensionality of it. And typically we stack all of our E vectors as columns of a big matrix E, and the dimensions are D, which is the embedding size, and N, the vocabulary size. Okay, so there's different ways to learn these embeddings. There's some standalone methods that learn them based on reasonable properties of text. But then you can also just have this matrix E as a learnable matrix within your model, and you can learn it with all the other parameters of your model so that it minimizes the loss function you're interested in. Okay, so if we want to use these embeddings, it's pretty straightforward. What we can do is we can stack the embeddings for a block size of t. So t is the number of previous characters we're using for prediction. We just simply stack the embeddings for the current, previous, and so on back to time t back. We stack those into a vector. Now that vector is going to have size or length td. And now that we have a feature vector, we can use any method that we know about. So in this course, we learned about logistic regression, we learned about tree methods, we learned about neural networks. Now that we have, just a real number feature vector, we can basically use any method. So just as an example, we talked about using a linear classifier, and we're going to call it an embedded linear classifier because it's going to be based on this embedding. And so here's one way to think about it. So here is our feature matrix, feature vector X that we constructed with our embeddings, stacking them. And then everything else is what we're used to. There's a bias and weight for K versus rest. And then we compute these scores. And if we want to make a hard decision, we just look at the biggest score, the index of the biggest score is what we report. So this would be if we want to do linear classification. You could also imagine doing something more sophisticated like an MLP, which has multiple stages of linear, nonlinear, and so on. And that should work better. And then the last thing we talked about is to try to make this expression a little bit more intuitive. We said, let's try to separate out the embeddings, which is one part of our design, from the actual token values from our training data. And so one way we can do that is we realize that we can write little ek as our E matrix times a one-hot vector where the kth element is the hot one. So if this is true, we can apply that like to write this like this, to write this one like this, and so on. So now we have what we call a block diagonal matrix. So we have blocks of these guys like that. And these are all the same E matrix, which is something we can learn. And then here we have our one-hot vectors that depend on our training data, our current batch of training. And this is not something we learn, this is just, the training stuff. So writing it this way is nice because now you can isolate the things we're learning from the things that our data loader is providing us. Okay, so if we're training this linear classifier, we would learn the bias vector of length n, which is the vocab size, the weight matrix, which is a matrix of size n by td. Td is the length of this. And then we have an embedding vector, which is of size d by our vocab size n. Okay, so you could imagine that this is something that you should be able to do with like PyTorch, is to train this model or train an MLP based on similar ideas. So this is where we got to at the end of the last lecture. Any questions on anything I've said? Okay, this is making kind of sense for where we are? Okay, so I just want to point out a couple nice PyTorch tools that helps with this kind of problem. And if you tried to code this from scratch, it would be, you could do so, but it wouldn't be using a lot of it wouldn't be in the style of what we did so far in this course. So far in this course, we were using blocks from the neural network library, like linear block and so on. And while you could implement this part with a regular nn.linear block, this part is tricky because you can see that the same parameters are being used for different things. And so people refer to this as weight tying, like these matrices you could say are like different matrices, but their weights are all tied together. So how do we actually do all this in PyTorch? Well, it turns out that PyTorch gives us a really nice way to construct vectors like this just with one line of code whenever you're using embeddings. And essentially what you do is it's called the embedding layer. The embedding layer takes in a vector of integers, like those t integers, and it basically gives you a matrix with these guys as columns. So it converts tokens to embeddings. And once you have those embeddings, it's easy to stack them and then feed them to your linear stage. Okay, so let's see how we do this. So this is the neural network embedding layer. So this is the PyTorch code for this kind of linear module. And so as usual, we have this initialization code that's run when you instantiate it, and then we have the forward pass. And when you look at the initialization code, when you instantiate it, you have to tell it the vocab size, which is n, the block size, t, and the embedding dimension, d. And then it stores a couple of these variables internally, and then it instantiates the embedding layer, which we know that embedding matrix is of size n by d, or d by n. So this is why we need to know those to create this embedding layer. And then we have a linear layer. And the linear layer is really just implementing this, or maybe implementing this. So it has a feature vector of t times d, and there's n possibilities of k. So here you can see that the linear layer is our t times d by n. Okay, so this is sort of how we constructed things in Unit 7. And we can see we do this again, but the new thing for us now is this embedding layer. Okay, so then how does the forward pass look? So what is given to the forward pass are integers, an integer tensor which tells us the tokens. So this can come from a data loader. We'll talk about that in just a moment. And this token matrix, it's a matrix of size batch size by block size. As we know, we typically train in mini batches, even though like this example just has one element in the batch. But in general, we train with mini batches. And then block size, as we know, is just T. So this is integer. And what the embedding does is it converts those integers to a real valued tensor. And the size of the real valued tensor is whatever this is, but then the last dimension is the embedding dimension D. Okay, so it just creates, for every integer, it basically it maps that to a vector, which is the embedding for that integer. Okay, and now we need to do our stacking. So we need to convert this 3D tensor to a 2D matrix. And so what we do is we just kind of combine these last two dimensions into, we do this simply by changing the view, just mapping it from a 3D tensor to a 2D. And this is done without changing anything in memory. It just affects how you look at the memory, so it's super fast. And then this is the flattened or stacked vector, and we pass that to our linear layer. So it's as simple as that. Okay, so this is how we can use embeddings in PyTorch, and if you do an MLP, then it's exactly the same. It's just that rather than a linear layer, you would go through your network at that point. So this would be, your network, not the linear layer. Okay, any questions on the embedding layer? Yeah.
So we define the block size like ourselves?
Yes, then block size is going to be a hyperparameter, right? So like you would imagine that the longer the block that you use for prediction, the better it's going to work, but the more complicated the model will be, right? Because you can see that this vector here grows with the block size, right? So your weights, you have more weights as your block size grows. So there's more parameters to train, but if you have enough data to train those parameters well, then it will work better. Okay, any other questions? Okay, same thing with the embedding dimension. That's another thing we have to choose. So these vectors become longer with bigger embeddings. And so with the embeddings, it's the same thing. Like if you make your embeddings too small, it means that you don't really have a very rich way to describe your tokens. As you make your embedding dimension larger, it allows you kind of a richer space to work in, but it also increases the dimensionality of what you have to learn. So there's a trade-off there as well. If you have tons of training data and tons of processing power, you can afford to make those things quite large. But if not, you're constrained. Okay. All right, so that's the embedding. Any questions more questions on embedding layer? Okay, the other thing that we have to think about is how we're going to make the dataset class for our integer valued token series. So if you think about how we did it back in Unit 7, we would make in NumPy a feature matrix. That feature matrix of where we have our training samples versus our features, right? We would make that in NumPy, and then we would just kind of cast it as a torch tensor. And then we would just, I think it was, trying to remember what the data loader was called, or the data set. It was called like tensor data set, that's what it was called. So you make a torch tensor, and then you just tell PyTorch, make a data set out of that. But let's think about what that requires now. So in this case, these are our integer values. So maybe 2, 3, 6. These would be the tokens that I'm using to predict the next token. But what this would look like if I have like a sliding window of tokens is it would kind of look like this. There would be this Toeplitz structure where the data is going to be, oops, you can see the data is kind of striped like this. And this is because in a time series, if I shift by one position, I just shift all the features. And so when you look at this, you can see that this is not completely efficient because we are kind of reproducing things. So like this 3 appears several times, the 2 appears several times. And in general, things will appear a total of t times. And so this kind of expands your data set by a factor of t in memory without actually adding any new information. So it's not really worth doing. So there's a smarter way to do this, which is just to produce these things produce each one of these vectors when they're needed by extracting them from your original data set without really creating this big matrix. And so we can do that just by a manual or a custom data set. So in PyTorch, if you look up the dataset class, of which tensor dataset is one, you can see that you can actually build them yourself. And if you build them yourself, you need to supply 3 methods. So there's the initialization function. There is the length, which basically, so this model can be called to say, what is the length of my data? And there's the get item, which provides an item. Like, for example, if the data loader wanted an item, this is how it extracts the item. And so, so here what we're doing is we just have, a long time series. And what this does is it just looks in there and it extracts a window for the feature and the next thing for the target. And it's basically just given, it's said, okay, so index is, this is like index. This is a location we should look at. And then it just looks at, it extracts the data starting in that position all the way up to index plus self block size. And then that's the X, and then the Y, the target, is index plus self block size. So it just, you tell it here and extracts this part of your time series and it returns it for you. So, and it also makes sure that it is formatted as a torch tensor when doing that of the correct type, which is a long integer. So pretty much that's all it does, but this is what you want to use if you're working with time series data, is to use something like this. Okay. All right. Okay, so any questions on the PyTorch? Okay, so the MLP code is exactly the same as what we saw a couple units ago. So the demo creates, it tries out 2 ideas. The first is a linear classifier. And I wanted to make the number of learnable parameters similar to the bigram so we can get sort of an apple by apple comparison, apples to apples comparison. And so the closest you can get is if you use a block size of 10. Remember the bigram uses a block size of 1 and an embedding dimension of 6. And the bigram uses an embedding dimension of 256, right? But in the bigram, the reason why, so the bigram, what it does is because the embedding dimension is so large, it needs to make the block size small to get this many parameters. Here, we're making the embedding dimension smaller than the vocab size, which allows us to make the block size bigger. So you could trade off these numbers, but this one gave a similar number of total parameters. So that's one of the methods that is coded and trained. And the other is a standard 2-layer MLP. The number of hidden nodes I chose as 4 times the vocabulary size, and it uses the GELU activation and batch norm. So after training and testing these models, so 27% was what we got for the bigram. So if we use this linear classifier with just similar but even a little bit fewer parameters, we get better performance because it's using smarter embeddings than one-hot coding. And if we use the MLP, then that improves on the linear method and gives us 45% test accuracy. And so now we're going to generate some characters, and we will initialize with a string that looks similar to the ones that you see in the data set. I don't actually know if there is a King John anywhere, but there's certainly different King characters. So with the embedded linear model, you see something that's kind of similar to the bigram. You see things that look like words, more or less, but they're not really words. And then like right at the beginning, it didn't do the right thing where we know that if you give it this, then it should immediately do a carriage return because that's the format of the data set. But in the embedded MLP, things are working a little bit better. So it does the carriage return after King John. And then you actually see some real words for the first time. But you also see a lot of, made-up words too. So things are getting better, but we're still pretty far from good. Okay, so then the next question is like, well, all right, what do we do from here? So one option is you could imagine, well, I don't know. What do you guys think? What could we do to make this better? You mean of the model parameters, or? Yes. So I can't remember exactly how it was initialized in the code, but you could maybe be a little bit more careful in how you initialize the layers of the MLP or the linear classifier, and that might get you a little bit better. But what if you wanted to make this like just a bunch better with kind of the architecture that we have here? Without really changing anything except some parameters, what can we do?
Would you need a overhaul if you wanted to, instead of a token being a character, a token is a word?
Let's say that we don't have the ability to do that.
We just do it bigger.
Exactly. We just scale things up. So like rather than using an embedding dimension of 6, we make that bigger. Maybe rather than a block size of 10, we make that bigger. So you can do this. And things will get better. But you'll find that things will kind of saturate and you'll start making these things quite big and it will be taking a long time to train. You'll kind of reach this performance ceiling where it just, you can't really, you're not really seeing much better performance past a certain point, and it becomes impossible to train. Okay, so that brings us to kind of the next topic, which is, well, how do we change the architecture to make this better? And the issue with our MLP is the MLP has a very generic architecture. It works, it's not really meant for any particular problem. It just works pretty well on a range of problems. But when we're doing time series forecasting, like that's particular problem with a particular structure, and the MLP is, it's just okay for that. So this is actually a subject people have been studying for many decades. And so if you look at the literature, you can see that there were a series of different models that were popular over different eras for time series forecasting. These are just neural network or deep network models. So one you may have heard of is recurrent neural networks, or RNNs. These existed at least since the 1980s, and they were superseded by these LSTMs, which I think started in 1995, and they were superseded by these gated recurrent units in 2014. So they were making improvements to the models. And so basically, we're not going to get into too many details, but these are all what we call sliding window methods, which is exactly what we've been talking about, where you have some time series, and then you extract your features, and you try to predict forward to your y, and you do this autoregressively. So you initialize, from your initialization, you generate your first character, and then you slide your window over, and you generate your next character, and you slide that window over, and you generate your next character, and so on. And so what the model does is it takes in this x, and it predicts, or it generates a y for you. So they all do that. Same as our MLP. The details are in how they do it and what happens inside their network, and how they're all different than our MLP is that they have memory. Meaning, so some time ago, the model was over here, and it was predicting this. Well, something about this x gets stored in memory so that the model kind of knows about this even at this time point. It has this internal memory that kind of memorizes, ideally a lot of what came before. Because the model is maybe not powerful enough to use a very large window, but maybe to do a really good prediction, you really need to know a lot about what happened in the past. So it does that by having some representation of the past stored as memory. And this recurrent one just kind of recurses and kind of updates that memory over time. It has like a state vector or something like that. But anyway, the problem with all these methods was that they all struggle to remember the deep past. And so as a consequence, they use more recent inputs here to predict y. They're not really able to remember these ones too well. And so that's kind of presents a limitation to these. And so the field is making progress, but it was, again, kind of like making slow progress at a certain point. Okay. So then, have you guys heard of any of these models? Okay. Any questions on anything so far? Okay, so there was a breakthrough in 2017 with a paper by Google researchers called Attention is All You Need. And this paper proposed an architecture called the transformer. And the transformer, instead of using memory as kind of the main design idea, uses something called attention as the main design idea. And I'll describe what that is in a moment. How many of you guys have heard of transformers? Okay. All right, a few of you, great. So the transformer is the architecture that powers like all the LLMs. Now there's various versions of it, but a lot of them are basically small modifications of what was proposed in this 2017 paper. Okay. So it's like a specific architecture that's not like linear activation like we learned about. It's just going to change those blocks a little bit. So we'll learn about how it's going to do that. But first, let's try to get some intuition behind this idea of attention. What do we mean by attention? So since we're studying character prediction, let's say that this is our context. We have a string of, or a list of tokens corresponding to this text string, the dog in the park run, and we want to predict the next character. Okay, so what do you guys think the next character is going to be? Just based on your knowledge of English. S, right? It's probably S. The word could be running, so it could be an N, but it's probably not going to be a space, or there's certain things that it's very likely to be like S. But then, how did you figure that out? Like, what actually went on in your brain to figure out that it should be an S? Right, well, you realized that this is a verb and that the subject is dog, and dog is singular. And so if you look at the plural, or you conjugate the verb, you realize that, well, if I have a singular subject, then it should be runs. So those are all the things you did, maybe unconsciously, but in doing that, and here's another example. If I change dogs to plural, and we do the same thing, we try to predict the next character, then it's not going to be S, right? It's going to be maybe a space or a period. So it's again the same thing is we were using our knowledge of English along with the facts that this sentence is really constructed by dog and run and plurality and stuff. And meanwhile, this phrase in the park is not really useful for our current prediction, right? It's not really affecting things much at all. So when we think about sliding window as the idea, sliding window in memory, these sliding window methods, they favor most recent inputs, and they kind of say, well, the most important things for predicting Y are the most recent things here, which is, for some time series, that's true. But for language, it's not always going to be true. It really depends on the language you're working on and how that language is constructed. And so all these models which favor most recent time, they struggle with using past time. And so they don't work as well as this attention mechanism. As I said, the later characters in a sequence are not necessarily the most important when we're predicting the next character. And if you think about what goes into actually doing a good prediction, it's kind of complicated, but most importantly, you have to understand the role of every character in the entire sequence to really predict forward. You have to figure out, that these are not useful, that this one is useful, and that involves, looking at these and understanding subject, verb, plurality, English conjugation, all that stuff. So the word that the community uses to describe the fact that these were important to predict this, these were not, is attention, and they will use this phrase, attends to. So a target attends to the tokens that are most predictive of it. So in other words, if this is the letter S, that's like, let's say in the training data, then you would say that this is going to attend to those characters and these characters. Okay, and in that sense, it comes attention. So every one of these characters could have like a numerical weight, where the larger the weight, the more important that is. And so those are called attention weights. And those are the things we want to figure out how to compute them. And that's where the transformer architecture comes in. Okay, any questions on attention as a kind of general concept? Okay, all right. So again, that's some intuition about attention. Here's some intuition about how transformers work before we even get into some details. So remember that the first thing we do is we have this string of characters. We convert them into tokens, which are integers, one for each character. And then, since we're going to be using embeddings for all the reasons we talked about, we convert our code book, which is our matrix of the different embeddings for each token in our vocabulary. We construct a real valued sequence from those embeddings. Okay, so that means like T is going to start out as, we look up the integer value. Let's say that's token value 5. So then we look at the fifth column in E, and we replace T with like this, you replace it with a real vector that is going to be, that fifth column. Okay. So we translate this character string to a sequence of embeddings. Convert the tokens of this to their embeddings. And so this sequence xi, the sequence xi will sort of be where we start. This is what the transformer will work on. And let's think about the information that's contained in the sequence xi. So as we constructed it, this sequence is just constructed by looking one character at a time and converting that to an embedding. So it kind of knows, okay, the first character is a T, and so T is used in various ways, in English text, and the embedding kind of knows about how T is used, and so on and so on. And like E is a good one because the letter E is used for very different things in English, right? Like sometimes it's used as a vowel inside, with like the sound E or eh, and other times it's used as like the last character in a word and not really pronounced and so on. So the embedding for E, for the character E, needs to kind of know about all those possibilities, but it doesn't know which one is being used at the moment. It just knows that the character E can do all those different things. So when we start, we have this sequence which only has the information really encoded in it about one character at a time. Okay, so it only knows about that character in isolation. And in order to really do a good next character prediction, we have to analyze this entire sequence and see how those different characters work with each other. And we have to do this by looking at the entire sequence at a time. So whereas a sliding window approach might say, like, my job is simply to take these and somehow do this sophisticated mapping here, the transformer is actually going to be like, okay, I'm going to take this, and I'm going to map this to another thing of the same length, where the new tokens in there, or embeddings in there, are going to be refined so that they have taken into account their neighbors, or actually all the other elements in the sequence, and now they are a more truthful representation about how that character is being used. So we're going to analyze the sequence, and we're actually going to go through several stages of this. Okay. So the transformer does this analysis over what we'll call L stages. At every stage, it takes the input sequence, which we're going to call X, and this is of the same length T as we've been talking about, and it's going to convert it to an output sequence, which we're going to call Y. So the first stage, it maps X1 sequence to Y1 sequence, and then it uses Y1 as the input of the next stage. So the Y1 sequence becomes X2, and then X2 is put through another layer of the transformer to get Y2. And then that is put through another layer to get Y3 and so on, all the way to YL. Every time you do this, you get a better sense of how the tokens are interpreting each other and specialized for their use in that sentence. Is that making sense? That's kind of the main idea. So the first time when you see this E used at the end of here, you don't really know what usage of E is that. But as you process the sequence and you realize, oh, this E is actually coming next to this T and H, oh, it's being used at the end of the word, blah, blah, blah. And you get this refined notion of what this E is really, what it really means in this block. Okay, so this is the main idea behind what the transformer does. Refines the tokens at every stage. Refines the embeddings at every stage. Okay. Some questions about this? Okay, so when you start, the vectors xi are exactly things you find in your code book. But as soon as you go through this first stage of processing, they're no longer vectors in your code book. They're just some, generic vectors of D dimension. Because E originally maybe has multiple meanings in your code book, but as you analyze the sentence, you realize that this E has a very specific meaning, and so the embedding as you go through here, gets refined and tells you what is that usage. Okay, so that's essentially how the transformer processes. At the beginning, we call the embeddings token embeddings because they come directly from our token matrix. But later on, they're called contextualized embeddings, and they're just some vectors in RD. So once you go through these stages and you finally have this sequence of embeddings that now you believe gives you an accurate representation of what every element of that sequence is doing, you want to come back to the token domain. So the first thing is you have to map these embeddings of dimension D back to logits of dimension N, your vocabulary size. So this is called unembedding. You do that simply by multiplying each one of these Y's by a matrix of dimension N by D. So it takes this D-dimensional embedding and it linearly converts it to an N-dimensional real vector. It can have negative entries, positive entries, so that's why it's considered a logit. It's not like a PMF entry. To make it a PMF entry, you actually take that N-length vector and you put it through a softmax. And that converts it into a PMF across tokens. So this is tells you this is the probability that this refined notion of the character E is actually the letter E versus some other letter or number or something. Okay, so that's first unembedded, second converted to token PMFs. And so now for every element in our sequence, we have a probability. And if I want to, and so if I want to generate something new, I could use these probabilities. Okay, are those steps pretty clear? Okay, now there's this one other thing that is sometimes used. It's called the temperature. So when you train, you just set tau equals 1. But when you use this for generation, sometimes people scale by this real number, positive number. And essentially, if you think about the way that the softmax works, softmax takes real numbers to probability, right? But as the magnitude of those numbers gets large, the probability gets much more peaked. And if the probability is really peaked, that means that it's not very diverse. Like if the probability is really peaked at one entry, that means, with very high probability, you will always generate that entry. So when you generate text, you might want to control the amount of randomness. Do you want it to only generate the most common or the highest probability thing, or do you want it to be a little bit free in what it comes up with? So this is something you can do in any kind of generative method. Is you can change the degree of randomness just by the temperature variable here. And you may have even seen this with some large language models. Sometimes they let you control this, and if you ask for it to be really random, it just gives really crazy stuff. Okay, it starts hallucinating, et cetera, et cetera. Okay, so that's the temperature. Okay, so this is how transformers work. We haven't learned about the details, but that's the high level. Processing this entire sequence several times to try to refine the meanings of every element in the sequence. And the meanings are all within this embedding space. And finally, to use them, convert them back to integers, you have to go back to the token space. And that's what's done here. Okay. All right. No questions? Okay. We're almost done, but let me show you then how this all works together with this picture. So let's say that we're doing character by character prediction. We have a block length of 4, so we take in these characters HELL, and we would like to, generate the next character. So the way that we actually do this is, here's our input sequence. We convert that to these embeddings where we know the dimension is D. There's something else called position embeddings. I'm not going to talk about it at the moment. But now we have a sequence of d-dimensional embeddings. We put that through several stages of transformer processing. And now we get these are our y's, our y sequence. And now we do the unembedding to get back to the dimensionality of our vocabulary and actually probabilities. And so, and our goal is to produce this target sequence. So for the first time, we're talking about how we actually train it. So we start with this sequence, and you can see we want to predict a forward shift, right? We want to predict a forward shift. So one way that we could train this was simply to focus only on getting this right. Because in our training data, we have the label. We have this as well as the true label, and we could try to do cross entropy on how good of a prediction this is compared to the truth. But it turns out that what the transformer does is a little bit more interesting. It actually predicts the entire sequence from this input. So in other words, it is going to try to predict this from this. It's also going to try to predict this from this, as well as this from this, and finally this from this. Now, if you notice, well, wait a minute, can it cheat? Can it just take these and learn to shift them? And the answer is it could. So there's some extra constraints that are placed in how you build a transformer so that it's not allowed to do that. But basically what it's doing is it's using H to try to predict a single character to try to predict the next single character. So try to predict one forward. Then it also uses H and E to try to predict L. Then it also uses HEL to try to predict the next L, and HELL to try to predict O. And so when you train this, you're actually training kind of like 4 things in parallel. 4 different prediction problems in parallel, which is great because number 1, it allows you to make more use of your training data. But number 2, you're teaching the transformer to handle sequences of varying lengths. So it can understand sequences of length t, but it also can understand sequences of length, shorter ones, because you're sort of training all those different sublengths. Okay, so that's how you train it. Any questions on that? Okay, and then how do we use it for prediction? Well, when we're actually using it, we're going to take in this input sequence, and it is going to generate a guess here. So for example, we might put in HELL, and maybe it generates not the correct thing, but ELBO. So you can see that it didn't predict this B correctly, because when it predicted this, it was actually only using this information or this information. So when we generate, we're going to force it to only use the last output and copy these inputs. So if this is the input sequence and this is our guess of the output sequence, we take these and this one, and we stack them together, and then we keep iterating on that. So for prediction, we only use the last predicted token, but for training, we train all of them simultaneously. Okay, sorry I went over time, but that's how it does text generation, but we'll see it can do other things as well. All right, so we'll review this stuff next Monday. On Friday, we have our third exam. Any questions on the exam? Okay, great. So I'll see you guys on Friday for the exam.